Section 9.1, Right Triangle Trigonometry. In this section, we'll be looking at the trigonometric functions of right triangles. Now, as a review, the trigonometric functions are basically functions who are equal to ratios of sides of a right triangle based on an acute angle. So in my picture right here to illustrate these trigonometric functions, I've chosen to talk about the angle down here. Now, based on the fact that the angle's down here, the side straight across from it is then the opposite to that angle. And likewise, the side here is the adjacent one. Now, had I chosen the angle up here, this would be the side opposite and this would be the adjacent. But based again on my image, we're going to go ahead with this angle down here. So this is opposite, this is adjacent to this angle. Now, the one side that never changes is the hypotenuse. So when we create sines and cosines and so on and all these trigonometric functions, we're basically going to talk about an angle and the ratios that any two of these sides together can create. And that's what these trigonometric functions are all about. So the first one, the sine, is abbreviated sin. Now, anytime you write the trig function's abbreviation right after it, you talk about the angle in question. So in this case, we're referring to our angle here as theta, which, by the way, is a pretty common variable for angles. So in this case, when I want to talk about the sine of this angle, we say sine of the angle, or sine theta, and that's going to be equal to the opposite side divided by the hypotenuse. Okay, so the sine function is defined to be for any acute angle in a right triangle to be the ratio of the side opposite, wherever this measurement is, divided by the measurement of the hypotenuse. Now, oftentimes this may be a decimal. It could also be a nice fraction if it does express rationally in a nice way. So just be prepared to understand it's a ratio, but you may see this number either as a fraction or written as a decimal. Now, the second trigonometric function, cosine, is abbreviated cos, and again, we always write of the angle. And the trigonometric function cosine is the ratio between the side adjacent to the angle and the hypotenuse. So this is going to be the ratio made by these two sides. Now, the one thing I want you guys to kind of notice about sine and cosine is that both of these involve the denominator being the hypotenuse. So with both of these right here, all these values are going to be less than 1. Because the hypotenuse, remember, is always the largest value as far as side lengths. So when that's your denominator, that's going to create the values of sine and cosine to always be less than 1. Now for our last one, tangent, the abbreviation is tan of our angle. And the ratio for tangent is the side opposite divided by the adjacent side. This is the only trig function that does not involve the hypotenuse here. So it's going to be opposite over adjacent. Now, one way you may have heard of before that may help you remember how to put these together is the acronym SOHCAHTOA. So if this right here is a nice little mnemonic device to help you remember these ratios, that's going to be a very important thing to be able to do. So SOHCAHTOA basically stands for sine being opposite over hypotenuse, cosine being adjacent over hypotenuse, and tangent being opposite over adjacent. So if this little device helps, that will really make a big difference because this is an incredibly important thing to be able to work with trigonometric functions. Now, you may not have seen these other three, cosecant, secant, and cotangent, because I know sine, cosine, and tangent are very common earlier on, but there are actually 3 others. Now, what makes these special is these right here, these are all the reciprocal functions. So that means in order to figure out cosecant, secant, or cotangent, what basically you're doing is you're just going to go ahead and take sine or cosine or tangent and take these ratios and just flip them, right? Find the reciprocal of each one. Now, the one thing you do have to remember, though, is which one goes with which one. So sine and cosecant go together. So sine is the opposite over hypotenuse. Cosecant is going to be the reciprocal of that. Likewise, cosine goes with secant, and tangent goes with cotangent. So these functions are the reciprocals, respectively, the way I've written it out here, of each one of these. So the abbreviation for cosecant is CSC, okay, of the angle. And that, of course, is going to be the hypotenuse on top divided by the opposite. So it's literally taking sine and doing the reciprocal. Now with secant, that's the reciprocal of cosine, it's abbreviated SEC of the angle, and that's going to be, of course, the reciprocal of cosine, which will be the hypotenuse over the adjacent. And lastly, cotangent is abbreviated COT, and that, when you do the reciprocal, will be the adjacent side of the angle divided by the opposite side. Now, when you look at all these, it's important to remember which one goes with which. So the way I sort of remember it is that S's and C's kind of pair up. So sine and cosecant go together, and cosine and secant go together. I think it's pretty easy to remember tangent and cotangent as they kind of share a name, but just remember that here is sort of opposites go together. S and C, C and S. Now let's practice using these trigonometric functions with a triangle that has actually some measurements in it. Now before we begin, it's important to understand that you do need to know all the sides of the triangle, okay? So because I know I'm working with this angle, I know the opposite side, I know the adjacent side, but I do need to figure out what the hypotenuse is. So as a review, if you're missing one side of a right triangle, you can always use the Pythagorean theorem. So I don't know the side that's the hypotenuse, but that will be equal to 24 squared plus 7 squared. So that means I got to figure out what's the square root of 24 squared plus 7 squared. Now we can go ahead and punch that up real quick. So we can simply take the square root of 24 squared plus 7 squared. And when you do that, it works out to be 25. So this one actually comes out to be a really nice number. Now sometimes when you do the Pythagorean theorem, you may not end up with really nice numbers. If that's the case, just go ahead and leave it in exact form. So if you want to write it as a radical, that's fine. Okay, so our job is to figure out all 6 trig functions for this angle, knowing these 3 sides. Okay, so let's begin with the sine of the angle. So the sine is going to be the opposite over the hypotenuse. So in this case, 24/25. And I'm okay if you want to go ahead and write that as a decimal, but I do want to remind you that you may see as a fraction, but if you want to write them as decimals, you may see that, just want to make sure you're comfortable. So if we did, 24 divided by 25, that actually worked out to be about 0.96. So just for this first one, I do want to show you that you may see them as fractions or decimals. It's common either way. Now, for what we're going to do, we do want to stick a little bit more with fractions because we're going to look at all 6, and to find reciprocals, it's a lot easier to look at them rationally. Okay, so let's do the cosine. So in this case for the angle, it's the adjacent over the hypotenuse. So it'll be 7/25. And then lastly, for the tangent of the angle, that's going to be the side opposite divided by the adjacent. So this would be 24/7. Okay, so we have our main kind of 3 original ones, sine, cosine, tangent. So now we want to figure out the reciprocals. So sine, remember, is the reciprocal with cosecant. So we're going to just basically take the 24/25 and flip it over. So that becomes 25/24. To find cosine's reciprocal, that is the secant. So the secant of the angle is going to be 25/7. And the reciprocal of tangent, cotangent, is going to be the reciprocal 7/24. Now, I did that without making any marks, but if it helps when looking at an angle, if you want to mark this side as opposite, mark this side as hypotenuse, and maybe give yourself a mark here for adjacent, that can always be helpful to make sure things go in the right place. And certainly on your paper, if you want to jot down one last time like SOHCAHTOA, if that helps you remember where things go as well, don't be afraid to give yourself, those little devices to make sure this all works out. So let's try one where we're looking at a little bit different given information. So I've given myself a blank triangle here as a visual aid, but the only information I'm actually given here is the idea that the sine of an angle is equal to 5/6. Okay, we're still going to do the same thing. I want to figure out all 6 trig functions, but instead of just giving me a triangle with a couple sides, they're giving me this information. Now, you can draw yourself a picture in any way. So I'm just going to go ahead and pick the angle down here. It doesn't matter which acute angle you use. So I'm going to call this theta. But what does matter is wherever you want to draw your angle, the side opposite that must be a 5 and the hypotenuse must be a 6. Okay, because if I know the sine of the angle is 5/6, remember sine is the ratio of opposite over hypotenuse. So that means if I choose to draw my angle here, this side here must be a 5 and the hypotenuse then must be a 6. Now, like before, I'm in the same situation where I'm missing one side. So in this case, I know the hypotenuse is 6 squared. So that's going to give me my unknown side squared plus 5 squared. Now, if I take 36 minus 25, that's 11. Now, there's no nice way to square root that, so I'm just going to refer to my missing side here as a square root of 11. I'm going to keep it exact so it'll be easier for me to write the reciprocals. Okay, so let's go ahead and find our 6 trig functions. Now, the first one's easy, right? We already know the sine of the angle, that's 5/6. So if I go ahead and look at the cosine of the angle, that's going to be the adjacent side here, square root of 11, divided by the hypotenuse. So this would be the square root of 11 divided by 6. Now the tangent, of course, is the opposite over the adjacent. So the opposite is the 5, the adjacent is square root of 11. So this would be 5 over the square root of 11. Now remember, that's not okay to leave your radical that way, so we need to rationalize. And when we rationalize, we'd multiply by the square root of 11 over the square root of 11. So the tangent really, when you simplify it, works out to be 5 radical 11 over 11. Now the nice thing is once you get sine, cosine, and tangent done, all we have to do is go ahead and flip each one over to get the reciprocals. Okay, so sine, remember, goes with cosecant, cosine goes with secant, tangent goes with cotangent. So sine, if I flip it over, we get 6/5. Okay, cosine, if I flip it over, we're going to get 6 over the radical 11, which again we need to rationalize. So when I multiply by radical 11 over that, we're going to get 6 radical 11 over 11. Now the thing about cotangent is, don't worry about our simplified answer. If you go back to the original setup and flip it, we actually don't have to worry about doing any simplifying. So just take this fraction and flip it. That way you don't have to worry about any rationalization. Okay, now we're going to talk about the idea of solving a triangle. Now, when we talk about solving, that just really means find all sides and all angles. So if you want to get yourself a note, all sides and all angles. Now, obviously, they have to give you some information to begin, and typically, because we know it's a right triangle, we'll be given at least one angle and one side. So when you think about it, we already know some angles and sides, so even though I'm saying all sides and all angles, out of all 6 of those things altogether, I'm really only missing 3 things. Now, as far as labeling, I do want to remind you something from geometry. Typically, I should say really all the time, capital letters are used to label angles, and lowercase letters are used to measure sides. So if this down here is angle A, we will always use lowercase a to indicate the side opposite, which means the side here at the bottom, that this 13, this is equal to little b, and that since c here is the right angle, the hypotenuse will be little c. Okay, so I want to make sure you realize, depending on how you're labeling your work, capital letters are going to be angles, lower cases of the same letter are the sides opposite that. So even if I didn't label it, if I talked about lowercase a, you would know I'm talking about the side opposite angle A, and so on. Okay, so in this case, we're going to have to use some solving. Okay, so we're going to use SOHCAHTOA as our setups, and then we're going to need to grab our calculator to maybe find what these values are, because they may not be nice ones, and we may have to work a couple things out. Okay, so first off, let's focus on what we need to find. Okay, so we already know angle A and angle C, so we're going to need angle B. We already know the side opposite B, so we'll need the side opposite A, and we'll need the side opposite C. So these are the 3 things that we're missing. Now, the easiest one to start with would be going after the angle, right? Because we don't even need trigonometry to do that. Inside any triangle, the angle sum theorem tells us that all 3 angles must equal 180. So that means that 34 and angle B here have to equal 90 since this one equals 90. So basically to find angle B, that when I add to 34, again, has to equal 90. So when you subtract, you can just take 90 minus 34, which is going to be 56. So in this case, angle B is going to be 56 degrees. That's our first one. If you want to mark it up here, that's fine. I'm just going to leave it down here. But that was the only one that really doesn't require trigonometry. Because again, when you're doing this, you don't need to worry about doing any sort of trig, since we can just use angle sum theorem. Now, to find the other ones, we're definitely going to have to use some trigonometry. So in this case, we're going to have to go ahead and say for angle A that we want to work with this angle 34 and then one of the sides. In this case, I guess I can only use the 13. So I want to use the 34, the A, and the 13. Now, this is where, again, SOHCAHTOA is going to play a really important role, so you make the choice of the correct trig function to use. So for the angle 34, A is the opposite, and the 13 here is the adjacent. So I need to find a trig function for an angle that deals with the opposite and the adjacent. So in this case, we're looking at tangent. That's going to be the correct one to use. So if I take the tangent of the angle, so the tangent of 34, that's going to equal the opposite A divided by the adjacent 13. So this is A over 13. Now, when you want to solve for A here, you just have to multiply the 13 over. So A is going to equal 13 times the tangent of 34 degrees. Now, when you go to your calculator and type this in, it's important to remember that your calculator needs to be in degree mode. So as you can see, my calculator is registered degree, so I'm good to go. Many of your calculators will also have an indicator on the screen. Mine actually reads out. Maybe it might be a D or a DEG or some sort of indicator on your screen that you're in degree mode, because you always want to know anytime you're dealing with trig functions what mode your calculator's in. So in this case, to find my side A, we'll just take 13 times the tangent of 34 degrees. And again, this 34 is right as degree since that's the mode. And it doesn't work out to be a super nice number, but I can go ahead and jot that down as about 8.77. So I'm okay rounding about 2 places. So actually, I'll write down here. So 8.77 will be fine. Okay, so we need to find now the last piece, angle side C. Now, technically, I could work with this angle A or angle B since I actually know what that is, but I really want to shy away from using side A. This was an approximation, and I want to make the best answer possible, so I'm going to avoid using A. I'm going to stick with the 13 since I know exactly what that is. And I like to always stick with the given information, so while I could use 56, whether, if I'm finding A or C, I'm just going to stick with the 34. So looking at 34, if I want to deal with C, that's the hypotenuse, and 13 again is the adjacent. So I want to pick a trig function for 34 that has the adjacent and the hypotenuse. In this case, cosine. So I'm going to say that the cosine of 34 degrees is going to be equal to the adjacent 13 divided by the hypotenuse C. Now, this is going to be a little different, right? It's not just a quick multiplication. I'm solving for C here, so I can't just, in one step get it by itself. Instead, what I'm going to do is I'm going to multiply C to the other side. So it's going to be C times the cosine of 34. And that, of course, then equals 13. And then, to actually get the value of C, I'm going to take 13 and divide it by cosine 34. So this would be 13 divided by the cosine of 34 degrees. Okay, so basically when you're solving for something on top, you end up multiplying to make that happen. But when you're solving for something here in the bottom of the ratio, we end up dividing. Okay, so let's go over to our calculator and take 13, and we'll divide that by the cosine of 34. And again, it doesn't work out awesome. We're going to round that to just a real easy 15.68. So in this case, this is going to be 15.68. And again, with angles, you're typically going to get a pretty nice answer, especially if you start with one. But with sides, go ahead and round two places if they don't work out very, very nicely. So let's talk about some special angles in trigonometry. The acute angles 30, 45, and 60 degrees are very special, and a lot of the foundational aspects of trigonometry are actually based off of them. Now, where we're going to work with them, since we're strictly looking right now at right triangle trigonometry, are 30, 60, 90 right triangles and 45, 45, 90 right triangles. Now, 30, 60, 90 right triangles actually come from the idea that you took an equilateral triangle and cut it in half with an angle bisector, segment bisector, altitude. So when you draw that directly down, it not only cuts this in half, it also makes a 90-degree angle and cuts the angle in half. Now, if we looked at the entire equilateral triangle, all the angles would be the same. They'd all be 60. So this one down here does remain 60, but when you draw that altitude, it also is an angle bisector. So the 30 will be up here. Now that should be easy to remember because just by the hinge theorem, the smaller angle should be opposite the shorter side, and likewise the larger angle should be opposite the larger side. Now, the other thing you have to realize as far as the relationship between the sides is that this hypotenuse here represents one side of that equilateral triangle we started with. So when you drop the altitude, this bottom side will be half of that. So the thing is, I could put an x there or an unknown, but the easy way to talk about it is to go with this here shorter side and simply call it a 1. And I do that because it gives me a really nice reminder about how big things are. So this is obviously 1. This will have to be twice as big. Now, in order to figure out this right here, which we're going to refer to as the long leg, we want to come up with a way to make that happen. So the way that you do that is you actually do the Pythagorean theorem. So in case maybe you've seen this relationship and don't actually know where it comes from, here's basically how it works. If I was to take those numbers that I just did on the triangle there and do the Pythagorean theorem, it would look like this. I would have to do 1 squared plus my long side squared would equal 2 squared. So this is 4. We're going to subtract 1, so that becomes x squared equals 3, and when you take the square root of that, we get the square root of 3. So this right here represents the relationships between the sides of a 30, 60, 90 right triangle. Now, that's fine and great, and that's how it works, but of course, you want to make sure you realize that depending on what side you're given, this is just how they're related. So however big this is going to be twice as big. However big this is will be radical 3 times as big as this. And again, as you can see how I wrote it, it's easiest when you relate it to the shorter side here. So I'm going to go ahead and take these numbers out because we've talked about where they come from. And I'm going to replace them now just with a very generic x, because that will give us sort of a template to solve any missing sides given this sort of scenario. Okay, so again, this is my shortest side, we'll call it x. Now, if this is x, of course, this is going to be twice as big, and whatever side this here x is, it's going to be x times the square root of 3. Now, the reason I really like writing it this way is now that when I look at any given triangle that's 30, 60, 90, if I want a quick way of solving sides, I can just look at what side I know and work my way around the triangle to figure out anything else. For instance, if I knew the hypotenuse, to go from here to here, 2x to x, you simply divide by 2. If I know this short side and I want to go here to the longer leg, you just multiply by the radical 3. And the other way works as well. If I knew the long leg, if I want to go from this measurement to this measurement, you simply divide by the square root of 3. And you can see that here. And likewise, knowing this, you can double to make that happen. So by writing it here, it gives you sort of a template to go from one side to the other, depending on what you know. Now, in a 45-45-90 right triangle, this is basically the idea of an isosceles right triangle. So because these base angles are the same, they're both 45, those legs of the isosceles triangle are also going to be the same. So in this case, it just is going to be an isosceles right triangle. Now again, I'm going to be really generic and call this just a 1, because technically that would be the shortest side, but this would also be a 1. Doing the Pythagorean theorem would say that 1 squared plus 1 squared would equal our hypotenuse squared, and 1 squared plus 1 squared is 2, so when you take the square root of that, that would be radical 2 big. So again, going back, if I go ahead and take the numbers out and more generically just talk about, knowing any side versus the other, I'm going to go ahead and go back to that shorter side and say, well, let's just call this x. And if this is x, this leg has to be the same. And going here, you just have to multiply by radical 2. And again, this can serve as a nice template when looking at the sides of a triangle. So if I know the hypotenuse, I simply divide by radical 2 to go to a leg. Or if I know a leg, I can multiply by radical 2 to make the hypotenuse. So let's try actually solving with one of these. Now clearly they don't need to mark a lot in here. If they give you a right triangle and label it 30, it's pretty obvious that this missing angle here would be 60. Now, once we get going on this, it's important to realize that you have to know where you're starting. So if you need to go off the side of your paper and maybe give yourself that little reminder, and this is just a little sketch you can make yourself, x, 2x, x radical 3. If you need to do that, that's fine. So here, I know the hypotenuse, and I want to figure out and solve the triangle. Okay, so I know my angles. I just need my other two sides. So here, I'm starting on the hypotenuse. I want the shorter leg. I want the longer leg. So again, by my template, if I want to go from hypotenuse to shorter leg, you simply divide by 2. So this would be 6. And then if I want to go from the shorter leg to the longer leg, you take the value there and multiply by radical 3. So this would be 6, radical 3. And again, I prefer exact answers with these sort of questions, so don't worry about typing it up. Now again, as a little template, as a little reminder, if I'm doing a 45, 45, 90, okay, these are my 45s. And then of course, whatever side this is, this leg will be the same, and then these legs times radical 2 will be the hypotenuse. So if this here is 12, this here would also be 12, and then this of course will be 12 radical 2. And because this triangle was labeled as isosceles, I would have to know these base angles would have to be the same, so that means that they would have to both be 45. Okay, so let's try a couple applications of using right triangle trigonometry to solve problems. In our first one, we're going to talk about the idea of indirect measurement. So in this case, we're looking at a situation where we're looking to estimate the distance across the lake from here to here. Now, when we do that, we basically are going to have to use some measurements taken by a surveyor where he put a stake here at the bottom of the lake, he put another stake over here at the far side of the lake, and then after going straight out from one of those stakes, we measure an angle between them. Now, I should say to some point across the lake. Maybe there wasn't a stake here, but we staked a spot, went straight across, and then we just looked at that distance and knew that we're looking through 24 degrees. So in this case, we want to use that to estimate what approximately would this distance here be. Now the thing is, we're obviously going to look to make a right triangle, so when you do this, fill that in to make yourself see those three sides, and then we're going to use SOHCAHTOA to make the decision on kind of what we're going to use. So in this case, as I take a look at it, it looks to me as if we have the angle here 24 degrees. We know that we're 750 feet away from that spot, so this is the adjacent side, and our goal is to approximate this right here, the opposite side. So I want to choose a trigonometric function that will deal with the opposite and the adjacent. So that would be tangent. So to set this up, we're going to say that we have the tangent of our 24 degrees, and that's going to equal the opposite, which is x, divided by the adjacent, which is 750. So when we punch this up, x is going to equal 750 times the tangent of 24. Okay, so we grab our calculator, and we're going to take 750 and multiply that times the tangent of 24 degrees. So rounding two places, it looks like it's about 333.92. So 333.92, and it looks like we're measuring this in yards. Now for our last example here, we're looking at the same sort of scenario with a surveyor, except this time we're going to be estimating the height of a building. Now what makes this kind of a next level problem is that we're given that the surveyor is taking a sight line from 5 feet off the ground. So it's important to realize when we make this triangle that the surveyor's line of sight is actually not along the ground, so we'll have to add that in later. So we're looking for the height of the building, and it looks like surveying from there, we knew that the angle of elevation was 22 degrees. Now, just as a reminder, anytime we talk about angles of elevation or depression, it's always measured from the horizontal. So horizontal up is an elevation angle, whereas horizontal down, this right here, this is the depression angle. So in case they gave you a question where they talked about an angle looking down, you would have to realize that the angle of depression here is an alternate interior angle to the elevation, and they would be the same. This angle up in here is never an angle of elevation or depression. So make sure you're always measuring from the horizontal when you do that. Now again, what we're looking at is the idea that we knew we were not only 5 feet off the ground, but the surveyor was 300 feet away. So this becomes about the exact same triangle as our last problem. So here, because we have the opposite side and the adjacent side, we're going to deal with the tangent. So the tangent of 22 degrees is equal to the opposite, which is x, divided by 300, the adjacent side. So when I punch this up, it's going to be 300 times the tangent of 22 degrees. And when I go to my calculator, 300 times the tangent of 22 degrees, looks to me like it's about 121.21. So 121.21 feet is the estimated height of the building.